Okay, we are rolling. So, I'm not sure exactly where I wound up last time. This may be a slide or two of duplication, but that's okay. We're going to hit this stuff pretty quick today. I want to get through this and maybe, I would encourage you, I sent you that link to the combined cycle operation on YouTube. That thing is pretty good. I may play a little bit of it in here. I can't. It's 54 minutes, so I can't play it all. But that guy has a series about Rankine cycle and all about power plants. And this guy is a power plant professional. Now, these things are high-level stuff. They are really good. If you search around, you know, look, I don't know what the name of this is, but anyway, if you can find that guy, I bet there's, I don't know, 5 to 10 videos. Some of them are even much longer than this, and they are quite good. Somebody, it probably says in the credits, Boiler Engineering Academy, whatever, somebody paid these guys quite a bit of money to put this stuff out there. It's been out there a little while, but it's pretty high-level stuff. So I encourage you to take advantage as much as you have time. We may do some more stuff. Probably will later on in the course. Okay, anyway, back to this. So Brayton cycle, you know, this was looking at increasing pressure ratio. So, you know, the initial cycle here is 1, 2, 3, 4. And these are isobars, these sweeping lines of constant pressure on a TS diagram. So let's say we doubled the pressure, whatever. So it jumps up from this level to this level. And so then the cycle would be 1, 2 prime, 3 prime, 4, back to 1. And we'll probably get the bouncing ball here in a second. But you can see the temperatures all go up. The lower side of it, the heat rejection, is the same. So this will improve efficiency for sure, thermal efficiency. Okay, so this shows how the thermal efficiency goes with the compressor pressure ratio. And so, you know, initially it goes up quicker, but still, even when we get over here, if we go from 6 to 8, 8 to 10, you know, I mean, we're going to get more efficient, because what's going to happen is we're going to get more temperature too. So, and as we get, every time the pressure goes up, these temperatures go up. And so that's all going to lead to greater efficiency. Okay. However, the downside is that there's a limit to how much temperature we can stand. And so we've got the little blue ball just showing that we're going up to higher temperatures. Okay. And you get to the metallurgical limit. Reliability, you know, when you buy one of these big stationary gas turbines, I mean, it's millions and millions and millions of dollars. You would like it to last for a while. And so if they put, you know, and of course you want it to be as efficient as possible. So if they push the efficiency too high, the temperatures go up too high, and then you start sacrificing on lifetime and failures and downtime. And so it's, you know, it's tough. And I mean, those calls are made by the manufacturer. You know, they're not going to put it out there at a temperature they don't think will be unreliable, but, you know, they're not perfect either. So stuff happens. Increasing. Oh, okay. So we're going to look and do an example here on the next page. Okay, so this is what he's getting to. So on this first cycle, 1, 2 prime, 3 prime, 4, my eyeballs don't quite work too well here. That's a high pressure ratio, and you see now we're capping the high temperature the same between the two cycles. So you see the dashed line across the top. So our max temperature is the same, but this is a high pressure line of constant pressure, and this is a lower, and this is my initial pressure that I'm starting at. So you can see this cycle has a much higher pressure ratio, and it has a significantly different shape than this one, which goes to the same temperature, but not nearly as high a pressure. And so then we're going to make some observations. we can see the shaded in area represents the work that's produced, the net work that's produced by the cycle, the turbine output minus compressor input. And so you see it's, we get different shapes, and we're going to have different efficiencies, right? This first one has a much higher temperature during the heat addition, so it's going to have a higher thermal efficiency, but this guy's got much more work coming out. So it's just interesting. So cycle A, greater pressure ratio, greater thermal efficiency. Everybody good? You drive up that average temperature between that heat addition. That heat addition is going on from 2' to 3'. Here it's going on from 2 to 3. It's not even close. Okay? So we know we'll get better efficiency out of cycle A. However, we get a larger net work per unit mass out of cycle B at lower efficiency. So the question is, what do you want? And the answer is, it depends on your application, what you're looking for. So, this last bullet says, for cycle A to develop the same net power as cycle B, you're going to have a larger mass flow rate and a larger system. Okay, but it'll do it more efficiently. So, and then there's a comment here about if you want turbine-powered vehicles where your size and weight constraint, you probably want cycle B, where you get more work, you get more push, even though your efficiency, you may have to buy fuel a little bit more often, but you'll get better performance. And that's just an example. So, okay, now we're going to talk about the irreversibility, the losses a little bit. Well, combustion is by far the largest. It's like totally irreversible. You can't undo combustion, right? Once it's burned, it's burned. You can't, they say that ship has sailed. It ain't coming back to the harbor. Okay. But we also have, friction and dissipative effects with the turbine and compressor that are significant. And so they, in the turbine, they decrease the work developed by the turbine. And of course, on the compressor, they're going to increase the compressor work, for the friction and all that stuff. And so overall, you're going to take a hit on both sides. Your turbine output's going down and your compressor input work is going up. So, you're going to get less out. Okay, on to the isentropic efficiency definitions. This is, I think we went over this for the Rankine cycle, and basically it doesn't change. It's just, we don't have two-phase to worry about. Where's the saturation dome on this one? Is there a saturation dome for air? Well, air is mostly nitrogen. Is there a saturation dome for nitrogen? Can you make nitrogen liquid? Yeah, there is a saturation. Well, why don't they show it? Where is it? It's a little bitty blip. It's way down here someplace. It's it just doesn't come into play. But yes, there is a saturation dome for nitrogen, but unless you're doing cryogenics, who the heck cares? You don't care. It just doesn't come into play. You're so far above and beyond that dome. This is just out in like superheated vapor land. So, but it's there. Okay, so remember how we do this. For a work producing device, we put the actual on top and the isentropic on the bottom because we want it to be less than 1. Okay, so in terms of the definitions there, and this would be the work per unit mass on both. And so for the actual, well, it's going to be what? We're going to go in at, this is, I can't find the turbine over here. We're going to go in at 3 and come out at 4 for the actual. But for the isentropic, that's straight up and down. We're still going to go in at 3, but we're going to come out at 4s. And that's the ratio. And it's the irreversibility that moves us up here. And so this S4 will be less, S4H, I can't talk, H4S will be less, a smaller number than H4, which is going to make this thing less than 1 because you've got the same inlet state at 3. And you got the same pressure. See, we exit at the same pressure, but we just have these irreversibilities that we wind up here at 4 instead of at 4S. Okay? So, and he's just going to put tags on there. So that's the actual turbine on top, and that's that process. And then the isentropic is there, and that's that process. So then it becomes quickly a matter of, can you find the enthalpies, you know, in the compressed air tables, that sort of thing, which is not real hard. We got a few example problems coming, but we're not there yet. Okay, so the compressor, we reverse it because this is work input, and the actual compressor requires more work input than the ideal compressor. So we put the actual on the bottom, and so the compressor starts at 1, and so it's going to go 1 to 2. So that goes down here in the denominator, and then the ideal compressor would go straight up at constant entropy. So it goes up to 2S, and so that would be this H2S minus H1, and they turn this around so it'll be a positive because these numbers up here are bigger than this number down here, so they just swap them around. It doesn't matter. You can put you can write the H1s first if you want to. Then you get 2 minus signs and they cancel, so it doesn't matter. Okay, and so that's the actual. There's the isentropic, and there's the isentropic. So y'all should, hopefully you're getting bored with this, that you've seen it enough. You go, oh crap, not this again, I know it. But, you know, it's a good review. You get to the FE exam, you may be glad you sat through some of this. Okay, so in a fairly simple gas turbine, there's a boatload of energy coming out. We got high temperature exiting that gas turbine. I mean, you're talking 1,800, 2,000 degrees. You're talking like, whoa, you can cook your dinner quick. You burn it to a crisp, you know? I mean, it's hot coming out. So if we don't do something, we're going to throw a lot of energy away. So we've got 2 possibilities to use this, maybe combinations of this, but regenerative gas turbines and combined cycles. So let's look and see. So a straight regenerator is just this heat exchanger, you know, and it's pretty simple. Well, guys, let's take we've got fairly warm air coming out of the compressor at high pressure, but we've got super hot gases at 4. Why don't we just put a gas-to-gas heat exchanger in and transfer energy from that's coming out at 4 and put it in to that air that's at 2 and heat it up before we go to the combustor, so the combustor will require less fuel to get to the same point. And so gas control for a combustor is temperature controlled. So T3 will have a set point, and so they'll control the gas input, the QN, based on outlet temperature. And so if we come in at TX instead of T2, and TX is greater than T2, then we just need less gas. It's simple as that. Put it in hot, use less fuel. And so let's cool it back down. And so we show the state Y on the exhaust gases going to atmosphere where we've cooled them down. So pretty simple. Oh, this is cool. Dueling red and blue balls. Oh, that's so much fun. We got to do that again. So, you know, and they kind of change, see, they change color a little bit as they come out. So the blue turns to purple, and red turns to, what is that? Is that Tennessee orange on the way out? Ooh. We can sing a little Rocky Top if you want to. What the heck? Anybody want to do a solo? Anybody do solos on Rocky Top? They'd probably fire me if they heard that coming out of here. Anyway, so, you know, preheating reduces heat added per unit mass, put less energy in. So what happens is we change the equations a little bit. So for the combustor heat input, instead of H3 minus H2, it just becomes H3 minus HX. And then that adds a step or two in the problem. You have to determine what HX is. It's an enthalpy greater than H2, for sure. And then without regeneration, then, you know, the combustor heat input has to handle it from H2 all the way to H3. So pretty simple. So now the output is not changed. We haven't changed anything on stage 3 or stage 4. And so we get the same work out, but we're going to put less fuel in, so the efficiency's got to go up. So this will enhance the thermal efficiency. Okay. So, you know, engineers, they always have to have parameters to evaluate everything. So we're going to use the term is regenerator effectiveness. And so what we're going to do here, the theoretical highest possible temperature for TX would be T4, because that's the hot gas temperature going in. You couldn't heat it. If you had an infinite heat exchanger, TX could not get above T4. It's impossible, okay? And it's not going to really get to it for any sort of a finite device. But so, you know, so we can get to there. That's what we can achieve. But the theoretical limit, this is cool. We get the stop sign. I think that's the first stop sign we've had. So anyway. Is with the enthalpy. Yeah, okay. Now that's an interesting statement. As the enthalpy of air varies only with temperature, is that true? Does the enthalpy of air vary only with temperature? No. Who said no?
Temperature and pressure?
Huh?
Temperature and pressure?
Well, that's true. That's not what I'm thinking of. Yeah, there is a small, that enthalpy is very, very weakly a function. But, okay, but we're operating under the ideal gas assumption. And so with the ideal gas assumptions, it does. But what I'm thinking about is like real air. What does real air have in it? Yeah, moisture. And so really, you know, like if you do the psych, and you know, God knows, you know, I love psych, you know, psychometrics. So, but if you take air at the same temperature and one of it's dry and the other is saturated, the saturated air has more energy in it because it's got all of that water vapor floating around in it. So to be strictly correct, he really should have said dry air, but I guess that's rolled up in his assumptions. But anyway, as a psych guy, when you see that, you go, well, just a minute here, moisture has an impact. And if you did this in real world, some of the calculations we did at Magnolia, yeah, we took we would take the moisture into account, I think. That's been a little while, but if we didn't, we should have, let's say that. Because it changes the numbers. Okay. So this is regenerator effectiveness. So that's the HX is the actual temperature that we heat that air to at the exit of the heat exchanger. And H2 is what it comes in at. And H4 is the enthalpy at the max. That's the enthalpy of the hot air into the heat exchanger. So that would be the maximum theoretical. So how close? So what percent are we coming to the maximum possible? Are we 50%, 60%, 70%, whatever? So if HX got to H4, then it would be 100%, which of course is impossible because you can't afford one that big. And even if you can't build one that big. So he says here, in practice, 60 to 80% approximately is what we get. It's an economic decision. So TX has to be below T4, which is at the turbine exit. Okay. So the decision is, you know, you buy a bigger regenerator, you save more fuel, but it costs you more on the front end. So that's an economic evaluation. And engineers, when you get out there in the real world, that's the kind of studies that engineers do a lot of. Like a company hires you and they say, okay, we know this boiler is inefficient. It could be an economizer on a boiler that takes flue gas and preheats feed water with it. So, you know, how big a one should we buy? The big one's 400,000, the littler one's 300,000. And of course, the big one gets you 40-degree boost in feed water, and the little one gets you 30-degree boost in feed water before it goes in the boiler. What do you think? So, I mean, you got to run your numbers. Hopefully you do a little model and you say, okay, you know, I can save this much energy and it saves this much money. And of course, then you got to project out the cost of your fuel and say, okay, and is that going to inflate over the next 10 years? I mean, you know, you don't know, but you got to make your best. Or maybe there's a corporate policy on how you model fuel price inflation, you know. And then you run the numbers and you go, nah, the payback is much better to do the smaller one than the bigger one, even though it saves more energy. So that's probably what they'll do, something like that. Okay, that's what we just said. Okay, so now we move on to another idea. So what we can do is we can add a reheat cycle, which is, you know, what we did in the Rankine cycle. We would do a partial expansion or through one turbine. We'd take it back to the boiler, heat it up again, then take it back to another turbine. Well, here it is. It's just with a Brayton cycle instead of a Rankine cycle. It's the same thing. So you see we come out of our compressor at 2, we go into the first combustor, burn some gas, heat it up. And so that's what that's 2 to 3. So this is constant pressure, heat it up to whatever our specified temperature is. Then we do an expansion from 3 to A. A's coming out of the first turbine. And see, that's ideal, right? Because that's isentropic. That's just going straight down. So we're just doing the ideal cycle here. Then we go back to another combustor and at some intermediate pressure. So this is the high pressure, intermediate pressure, low pressure. And so then we're going to heat it back up again to some temperature. I mean, it could be that we heat it all the way back up to 3. You know, I don't know. It's just however they designed the cycle. We're going to expand again, and then we're going to basically, we're going to throw it away and bring in some more. But we think about this as a closed cycle with heat rejection to the environment. So, you know, pretty much the same thing. 2 turbine stages. And so you can see the 2 cycles. If we do it without reheat, it's just 1, 2, 3, 4 prime 1. If we do it with, it's 1, 2, 3, A, B, 4, back to 1. And of course, so the reheat cycle, we've got a larger enclosed area. So we're going to get more work per unit mass, which is the aim of this. So there's that shaded area represents the work output of the cycle. You know, net heat equals net work for a cycle. And that is without the reheat. And, oops, thought we had another one there. Okay. And so that's what we're going to get out of this. Okay. Another thing to notice is look at the temperature that we exit the cycle. On the basic cycle, we exit at 4 prime, right? And on the reheat cycle, we exit at 4. Well, 4 is hotter than 4 prime for sure. Now, if we didn't do anything, that part of that loss would be increased a little bit, right? Because we'd be throwing more heat away. But what we can do then, we can put regeneration in. And so then we have a higher temperature going into the regenerator. We make the regenerator work better. So what we're going to see is we've got multiple components here, and we start adding and we start really boosting the work and the efficiency of it. Of course, we also boost the cost of it, and the manufacturer likes that because he gets to sell us more hardware and he gets to make more money. And of course, in the long run, we probably get to make more money because we have, you know, a better piece of equipment. But, you know, there's always trade-off. So that just shows the temperature difference between the two. Okay, so reheat and regeneration used together. So we get increased thermal efficiency. So that's a pretty good pair. Okay, another possibility, and I'm sure you've probably seen this before, but it's to break up the compression process into multiple stages. Air compressors, better air compressors that want more efficiency will, you know, if they're going whatever the pressure range, they'll take half of it, come out of that first portion, cool the gas down, and then go into the second stage. So as we do this intercooling, we increase the efficiency of the compression process. Okay, so that's what it looks like. So let's take a look. And this, again, this is ideal stuff so that the work, you know, say our basic cycle is 1, 2 prime, A, B, 1. And so this is a line of constant entropy, and this is all reversible and adiabatic. And so that enclosed area is the work required by the compression process. So we're going to show this on a PV diagram. And so process 1 to C. So we're going to go the first stage of the compressor. So we go through the compressor and we go up to C. And this, they're calling that intermediate pressure just P sub I. And then we're going to cool it. So we got some sort of probably air, just taking ambient air. It could be cooling tower water, you know, whatever. But we're going to cool that flow and get to D. And then we're going to compress again from this intermediate pressure at temperature D, and we'll come out there. So that's what it looks like with the intercooling. And of course, the whole big cycle we already talked about is without intercooling. And so we see that with intercooling, that dark brown area there is the work input. And without intercooling, that's the work input. So guess what? That's what we save by doing the intercooling. So, you know, probably a good investment. So if this doesn't change, well, if the work out of the turbine remains the same, then let me see, if the total work of the turbine remains the same, reduction in compressor work, yeah. So if we get the same out of the turbine, we subtract off less for the compressor, then we'd have an increase in net work. Okay, so then we can do intercooling with regeneration. And so this is, let's see, compression and without intercooling. So let's look at this. Okay, so comparing states. There we go. Okay, so if we don't do the intercooling, we just go straight up. And so this is the temperature. It's at T2 prime. If we do intercooling, we come up and then we cool back down to D and then we come in here. So clearly T2 is less than T2 prime. So again, and now if you didn't do anything else, then that would be a cooler temperature, into your combustor. But they say, yeah, but whoa. So this enhances the potential for regeneration. So again, this makes the regenerator work better. So if you pick just one of these things by itself, you may have some competing mechanisms, but if you team them together properly, you can make the whole system better. So that's kind of what we're getting to. Okay, and now he's talking here just as far as the temperature limit, assuming that we're using air. And see, this is the inlet air condition at 1. So there's no way that TD could be less than T1 if this is what we're using as the cooling medium. Now, if we were using cooling tower water, then maybe we could, but he's not, and that's a definite possibility. But at this level in these slides, he's not taking that into consideration. So, that would be something you could look at a plant. Maybe they were running their intercoolers with ambient air, but if you had cooling tower water or lake water available, you could put in a different heat exchanger, you could pump colder water through there, you could get a lower temperature, you could reduce the compression requirement, you could run the numbers on that. What would it cost? Now, at a power plant, everything's expensive. But, I mean, the numbers are just big. That doesn't mean the concept's not good, and it doesn't mean it might not have a decent payback. So that's the kind of thing that you can investigate. And that's just showing that, TD can't be below T1. So that's the point of this. Okay, so shown here is a regenerative gas turbine incorporating reheat and intercooling. Looks like a good homework problem to me. What do you think? Miles, you excited about that one?
Those are words.
These problems aren't too bad, but you see how it all goes together. We split the compressor into 2 stages. Intercooling reduces compressor work. We got hot gas coming out at 9. We put in the regenerator. We come out of this first stage of, or the second stage of compression. We're going to boost temperature, which reduces the heat, the combustor 1 heat input. We come out of that, and then there's nothing, no augmentation from 7 to 8, just additional heating. But we're reheating, and we know that helps us. So a lot of stuff going on in the cycle. Okay, so we get what? The net work outputs increase. We get better efficiency. Okay. What are we going to do? Oh, okay, yeah, we're going to write the equations. Okay, so just kind of, you just have to be able to look at the diagrams and identify the states, right? So the expansions come down. 6 to 7 is an expansion, and 8 to 9 is an expansion. So H6 minus H7, turbine work. H8 minus H9, turbine work. Okay? And this is handy to remember. This can save you some time working problems. Instead of going to all the trouble to actually find H7, if all you're looking for is turbine work, then you can just find H7S and H9S. And if you're given the isentropic efficiency of the turbines, you can just plug that in and it will give the same result. So that's a handy little trick to remember. That's worth knowing. And likewise on the compressors, look for the dotted lines. If they're coming down, it's a turbine. If they're going up, it's a pump or a compressor. And so the first stage is what? H2 minus H1. H2 is bigger than H1, so they write it that way. And the second stage, H4 minus H3. And on this one, you do the same thing, but don't forget, you gotta divide by the efficiencies here, okay? Because when you write the isentropic efficiency, you flip where the isentropic compressor is versus the actual, okay? Bingo. So then for the heat added, where are we adding the heat? Okay, we're adding the heat from 5 to 6 and from what, 7 to 8. So H6 minus H5, H7 minus H8, just what you'd think. Regenerator. Okay, so what's the, don't peek. What's the regenerator? So that's going to be what? We come out of the regenerator at what, 5? We went in at 4, and the maximum would be, so H5 minus H4, I think, minus H9 minus H4 is my guess. Of course, I looked at this earlier, so I cheated. But anyway, that's what the regenerator effectiveness is. And what, T3 can't be less than T1. So that's what we said before. Okay, any questions on this? Yep.
So is that the hot fluid and that's the cold fluid, that's T?
Okay, because 9 is what's going into the regenerator. Okay. And 4 is what's going in on the other side. So the maximum potential is to heat 4 all the way to 9. That's what we divide by. What we actually accomplished was we heated 4 to 5. There you go. Yeah, good question. Anything else? Okay, so combined cycle. Well, he's talking up here, you know. Well, he's just saying that, you know, if we don't, the old comment about if we don't do anything on the Brayton cycle, we got all this hot gas coming out, which we'd be throwing away. So there's two ways: the regenerative stuff we just went through, and the other is the combined cycle. So we'll see what this is. So there's our first combined cycle. That's about as simple as you can draw one. Okay. So we've got the Brayton cycle up on top, just compressor, combustor, turbine, putting out a whole boatload of energy at 4. So this is going to be the heat input to our boiler, which is called a heat recovery steam generator.
Can you see these slides out there?
Do what now?
Can you see these slides out? We don't have the combined cycle.
Oh, really? Damn. Dadgum right. You don't have this? I am chagrined. Well, I tell you, yeah, let me see. I'm connected. Well, here, I tell you, y'all take, I'm pounding you pretty good. Take 5 and I'll print these, and then I'll do both. But I can print them right now and it won't take that long. So, goodness gracious, what slide is this? This is 48. It's only 48, 49, and 50. It's only 3 slides. Crap. As we said, I screwed the moose on this one. What am I doing? I don't know what I'm doing. That's what I'm trying to do. Okay, print. Oh, I can't print. Oh, okay. I got to go print this from my. That's right. I can't get to the computer here. Well, y'all go ahead and take me. It won't take long. I got to print them from my office. Yeah, go to the bathroom, get a drink, whatever. Don't leave. I'll be right back. I think I'll stop the recording for a minute. Well, it's good to give them a rest break, you know. All right. What in the world is that? Hello. What is this? I want to close it, open it again. That was strange. If this happens again, I'm going to quit for the day. How weird. I can't hardly. That is weird. I don't know. Probably have some virus. Well, we have that recorded for posterity. Whatever. Phew, this is hard. I can't say that. I have to censor myself every once in a while. I could get in trouble for that one. Okay, now let's go on to the combined cycle, where we have teamed this Brayton cycle with the Rankine cycle, and the boiler becomes, in this simple example, just a heat exchanger. In reality, we call this an HSRG. All right, team, what's an HSRG? Heat recovery steam generator. And they can look a lot different than boilers, but it becomes the boiler in this example. And so, you know, when you want to know what's, this is where these two cycles meet, is in this heat exchanger, which is the heat recovery steam generator. Okay. So there you go. Serves as the boiler for the vapor power cycle. And in thermodynamics parlance, vapor implies phase change. Gas turbine cycle implies no phase change. That's why there are different chapters in the thermo book. One is vapor and the other is gas. Okay, so, you know, speaking of our temperatures of heat addition and reduction, so the Brayton cycle has a really high average temperature during the heat addition. That's characteristic of gas turbines. And the Rankine cycle, because we come out of this lower turbine at such a low pressure, this is, you know, 100, 110 degrees Fahrenheit, we have a very low temperature, average temperature of heat rejection, and those two facts combined are going to lead to a very high cycle efficiency. So in thermodynamic parlance, which I know you want to be up to date on your jargons, or your thermodynamic discussions. So the thermal efficiency is greater than if we didn't team these two things together. And there's a lot of combined cycle power plants worldwide. This is TVA's go-to right now. So on all these homework write-ups that I am bludgeoning my way through your homework. That stuff's brutal to grade. But anyway, a lot of you selected natural gas. And I think that's probably would be the decision right now. If they had to put a big power plant in central Tennessee, it probably would be a combined cycle. And you know where they'd put it? Real close to the pipeline, where the big gas distribution lines run. They pay a lot of attention to where can they be guaranteed of enough gas, you know, that you had a big enough interstate transmission line close. Yeah, that was anywhere halfway near the area. And you had transmission lines, all that stuff plays into it. Okay, so guess what? We have a net work out of the gas turbine cycle. And so that's gas turbine work output minus gas turbine compressor work input. So that's net. And on the vapor cycle, it's the steam turbine work output minus the pump work input. So you got to take out all in consideration. And the input, the way this is drawn, is just into the combustor. Now, in reality, these heat recovery steam generators usually have what they call duct burners, and they can inject additional heat. They can burn additional natural gas to heat up that turbine exit 4 to a higher temperature before it goes into the steam generator. And so they'll run that duct burner during times when they need extra generation capacity. So you have some baseline generation without the duct burner, and then they'll probably get an extra 20 or 30% out of the unit if they fire the duct burner. Oh yeah, on the yeah, what they do, they will take those exhaust gases, and there's a heat exchanger, it's called the economizer, that's at the tail end. And so it takes the water out of the condenser, the makeup water and all that, and then that's a stage of feed water heating. That's probably the only stage of feed water heating, you know, but yes. Very good, good question. Okay. So for adiabatic, which means, you know, we don't have any stray heat losses. And so when you work a problem like this at this simple level, you know, this is where you join the cycle. Usually you'll know a mass flow rate either on the Brayton cycle side of the air or on the water side. And this allows you to calculate the one that you don't know after you've found all of the enthalpies. So, you know, down on the bottom cycle, on the Rankine cycle, that's m dot, calls it V. It's water in at 6 and it's steam out at 7, but that's the m dot V. So times that enthalpy difference has to equal the mass flow rate of the gas times the enthalpy difference on the gas side, which is H4 minus H5. And so the heat lost by the gas goes in to the steam, generates the steam, drives the Rankine cycle. So pretty simple, really. Just a lot of stages. You can make a big nasty problem out of this. Woo, could you ever? Y'all want to take home test? Be careful what you wish for. You get 18 feed water heaters, you go, oh God, I don't want to do this. Okay. Europeans, not so much of this in the States, but a lot of other countries where people are closer together. You know, we want to put our power plants out in the middle of nowhere where there's really no use for low-grade heat. But in Europe and all, a lot of the power plants are built right in the population centers. And so they'll use some of this low-grade energy to heat homes. So that's what they're talking about here. Well, I think we've talked about this before. But so what they're showing is, you know, just the Brayton cycle here producing some electricity. Then we generate the steam. We come out of a steam turbine with enough temperature for this to be useful. If this is if this is 100 10 degrees Fahrenheit, it's not hot enough to really be useful. So this has to be designed into the cycle. Maybe we come out of here at, 100 pounds is what, 327, I think. 100 PSIA is like 327. So that would be like 85 PSIG would get you 325 to 330. That's plenty hot enough to heat your home. You probably don't have to, you could probably come down to maybe 50 PSIG or A, whatever, and still have enough temperature to make this useful for space heating. So then, now in this diagram, they're showing a condenser, and so we just have a water loop circulating through this, which in this case, it shows it generating steam. It could just generate hot water, whatever, and it gets pumped off to town, and people pump it into their houses, and that's how they heat. Okay, and then, so then the condensate stays here and goes here. There's lots of different variations on this, but that's kind of what it's talking about. Oh, and we get the little ball around in a circle. Okay, so get the power, the work makes electricity, and so we turn on the lights and we keep them warm. So anyway, so that's it on that. Okay, so let's do this. We got just a few minutes. I'm going to play a little bit of this. Yeah, I don't know how many of you have watched some of this video. I know I was talking to a few people that have watched it, but we only have a few minutes. But I want to whet your appetite that this really is pretty good and is something that I think would be very beneficial for y'all to watch. So we'll just watch a few minutes. It's a little blurry, but.
Up to this point in this video training series, we have focused upon the operation and maintenance of simple cycle gas turbines, which discharge the turbine exhaust gas to atmosphere. We shall now move on in this video to examine the combined cycle, which includes both gas turbines and steam turbine power generation. As we saw in earlier days, the combined cycle system employs many different arrangements. Utilize the relatively high amount of energy which is contained in the exhaust gas leaving the gas turbine.